Hello friends, welcome to GT Science tutorial. In this video, I'm going to talk about solid solutions. This is going to be a very important concept. In my previous video, I have already talked about different types of defect in their mathematical calculations, including vacancy defect, Schottky defect, and Frenkel defect. And in my other video, I have already talked about different types of impurities in a crystal. They are substitutional impurity and interstitial impurity. Now in this video, I'm going to talk about solid solutions. So let's start. So let's see what solid solutions actually are. First of all, we need to understand about solutions. Solutions are the homogeneous mixtures of two or more component, right? Suppose we take water in a beaker. This is water in a beaker. And if we put sodium chloride, if we put sodium chloride in it, then what will happen? It will form a solution, right? It will form a clear solution. That means the sodium chloride will get dissolved. We call it homogeneous mixture. It is now a single phase solution. That's what means solution, right? And sodium chloride here will be called as solute, and this water will be called as, this is water, it will be called as solvent. And solvent plus solute will be equal to solution if that is a homogeneous mixture. Now in solid solution case also the concept is same. So solid solutions are homogeneous mixtures of two or more crystalline solids that share a single crystal lattice. Similarly, this means that the atoms or molecules of the different components are distributed uniformly throughout the solid, forming a single phase. It simply means that suppose we have like copper. Similarly, copper. So this copper that we just arranged in their crystal lattice, that is brass, right? That is brass. But we take, if we take zinc as impurity or another phase or solute, then what will happen? This zinc will come over here, and what will this zinc do? This will just replace, zinc will just replace this copper, and it will occupy this position. Now, like as we are seeing in atomic scale, it seems different, but if we see in bulk, like if we see from outside in real world, will we see this zinc atom over here? No, we won't see. That is, a solution has been formed. In this case, this will behave as solute, and this whole bulk will behave as solvent. So small amount of solute came over here, stayed over here, and made a solution that is called a solid solution. Now let's see the types of solid solutions. Types of solid solutions. First of all, let's understand about substitutional solid solutions. Substitutional, we already know the meaning of this, substituting, right? Look at here. Suppose there is a crystal lattice A, 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 and A. This is the crystal lattice. Another B is over there. Now this is the impurity or the solute. Suppose the atomic radii of these two is almost comparable. Then what will happen? If we mix it over here or if we bombard it over here, it will just replace one of the it will just replace one of the crystal lattice atom, that is A, and it will eject it out, and in that place it will just go and situate itself over there. That means B will come over here. This is substitution, right? So substitutional solid solutions, in this type, atoms of one component, that is atoms of one component substitute for atoms of the other component. Atoms of one component will be substituted for the atoms of another component in the crystal lattice. Similarly, this is most likely to occur when the atoms of the two components have similar sizes and electronegativities. I've already told you their sizes should be comparable. The size difference should not be more than 15% range. Okay, that their size difference should be within 15%. Not only that, the electronegativity should not be high as well. An example of that is an alloy brass. Brass means, we already talked about this, copper, a crystal structure of copper in which a zinc atom comes and just replaces one of the copper, and it will take that position. It will substitute one of the copper atom. Now this is called brass. That is the example of substitutional solid solution. Similarly, another one is interstitial solid solution. So interstitial means, look at here. Suppose we take, wait a minute. Suppose we take a crystal lattice of some atom or ion. Now now these positions, these positions are called interstitial positions. Okay, these positions are called the interstitial position. Now look at here. If another atom, atom that is solute, which is very small as compared to this bulk atom, tries to get inside or is bombarded inside, it will not replace another atom. Rather, it will just take an interstitial position. This is called interstitial impurity. So interstitial solutions, let's understand that in this type, atoms of one component occupy the interstitial sites. This component is occupying the interstitial site, that is the space between the atoms in the crystal lattice of the other component. Similarly, this is most likely to occur when the atoms of the solute are much smaller than the atoms of the solvent. I've already told you, atoms of the solute will be much smaller than the atoms of the solvent. And an example of an interstitial solid solution is steel, which is a mixture of iron and carbon. So iron is larger in size, iron is larger in size, carbon is smaller in size. So when carbon is mixed with iron at certain temperature, then iron with the carbon atom will go and take the interstitial position, forming steel. Steel is homogeneous, right? But this, that is actually the mixture of two components, so we call it solution. What type of solution? Interstitial solid solution. I hope you understood everything about this video. If you like the video, please share this video as much as you can. And thank you for watching the video. And don't forget to subscribe the channel. If you subscribe my channel, my face will be like this. Thank you. Bye bye.